Yeah, it's fine. You can see. Okay, so I won't turn the lights on. Okay. All right. Okay, so hello everyone. Welcome back. There's not many of you today, which is odd because I said I would talk about the midterm. So I guess people don't care about the midterm. Okay, so before we get started, as usual, I'd like to give you another Italian expression. Is the mic working? Yeah, it's working. So today's Italian expression is also about a toad. So remember, on Tuesday, we saw an Italian expression which was about swallowing a toad. So today, it's going to be slightly different. It's going to be about doing something else with a toad. So the expression for today is sputare il rospo. So what does sputare mean? Sputare means to spit. And then as we saw on Tuesday, il rospo means the toad. So the literal translation is to spit the toad. Okay, well, what does this actually mean? How do you actually use this? So this is typically used to tell someone to speak up. So to speak up, something that you're doing right now, which I'm a bit annoyed by. Ah, good. So when you want to tell someone to speak up, you say, why don't you spit the toad? So what's an example of a sentence in the context of this class where I could use this? So this is my sentence. So Kesre is happy that many of his future students are comfortable enough to sputare il rospo during class. So I'm very happy that many of you speak up and ask questions during class and make comments and make corrections. I'm very happy about that. Okay, so off to slightly more serious announcements. The first one is that assignment 1 has been graded, and I will post the grades sometime today or tomorrow. But the grades are excellent. So the median is like something like 95, and the mode is like 99 or something. So I'm not really worried about people understanding basic discrete math. So this is very good. Presumably everyone did it by themselves, so that's why I'm not worried. The next thing is that assignment 2 is due today. Assignment 2 is due today. And assignment 3 will be released tomorrow. And it will be due in 2 weeks from now. Okay, and the last thing is, because I said I wanted to talk about the midterm, I want to talk about the midterm, but I'll probably get sidetracked with explaining to you the pumping lemma stuff. So at 9:45, why are people still talking? At 9:45, could someone please raise their hands and remind me to stop talking about whatever I'm talking about and to talk about the pumping, not the midterm, okay? So even if I say, no, give me like 2 more minutes, you have to be very brutal. You have to be like, no, we have to talk about the midterm, okay? So like Owen, can you do that? Okay, Owen and Louis, okay, for redundancy. Louis is not paying attention. Okay. Oh, good. Oh, okay, excellent. Thanks, Louis. Excellent. Okay, good. So off to the material for today. So today we're essentially going to continue what we started last time, which is using the pumping lemma to prove non-regularity. Okay, so if you remember from Tuesday, what we did is we saw the pumping lemma. So the pumping lemma is a statement like this. I won't write it down right now. I'll just write PL for the pumping lemma, but I'll write down the conditions in a second. Essentially what it was saying that if L is regular, then L satisfies the conditions of the pumping lemma, right? And so the pumping lemma for regular languages, because we're talking about a class of languages which is regular. Okay. So you were probably wondering, how is this exactly going to help me to prove non-regularity? So this is a very common trick in sort of theory of computation and more generally in studying formal languages. The idea is what we've created here. We've created a necessary condition for regularity. So in other words, if L is regular, it necessarily must satisfy this property here. Whoops, no. This property here. Okay, so it must satisfy the conditions of the pumping lemma. So this is what we mean by a necessary condition. And we're going to see this several times. So there's a necessary condition for a language to be context-free. So if a language is context-free, it necessarily has to satisfy some condition, which we'll see in about a month, to prove that a language is not context-free. So you can do the same thing. You do the same establishment of a necessary condition for context-free languages. And you can also do it for something that we're not going to talk about, but which you talk about in computational linguistics, which is strictly local languages. So in case you're interested, do take 445. Okay. Right. So I have these necessary conditions for, regularity, context-free languages, strictly local languages. How does this really help me? Well, the idea is if I know an implication is true, then I also know its contrapositive is true. So the idea is if I can show that, for instance, in this case, L does not satisfy the conditions of the pumping lemma, then it cannot be regular. Okay. Because if it were regular, then it should satisfy the conditions of the pumping lemma by the pumping lemma, but it doesn't, so that's a contradiction. So that's another way, Ryan, that's another way of thinking about it. Good, okay. So this is the general setup. So essentially what we're going to do now, we're going to sort of revisit the pumping lemma. I'm going to rewrite it, and we're just going to take its contrapositive, and we're going to see how we can show that the negated, let's say, premise of the contrapositive is true, and we're going to use that to show that the language is not regular. Okay. So what is the negation? So remember, right, we have the pumping lemma. It says if L is regular, then something, something. So now we have to negate it, right? We have to take the contrapositive. So we have to sort of flip the premise and the hypothesis and then negate both sides, negate both statements, right? That's the contrapositive. So what is the contrapositive? Contrapositive of the pumping lemma. Okay, well, to see this, we need to revisit what the pumping lemma says. I'm going to rewrite it. So the pumping lemma for regular languages. This is just sort of a recall from last class. Suppose I have a non-empty alphabet and I have a language over that non-empty alphabet. Then what the pumping lemma says is if L is regular, then there is some positive natural number for which, for any string in L with length at least p, you can decompose that string into 3 parts, x, y, z. So W is equal to x, y, z. Where, remember that there was this idea of a cycle. So x, y is going to be the bit by which you must have a cycle. So that has to happen within the first p letters. Okay. And if you have a cycle, then the label of that cycle is y. So because you have a non-empty cycle, then the length of y is strictly greater than 0. And then you can decompose the string, any string w, such that for any integer I you pick, and of course, I has to be a natural number, it can't be negative. Then I'll say wi, which I'll set to x, y, I, z. And so typically what we refer to x, y, I, z as is the pumped string, okay? Because what you're doing is you're taking x, y, z, and you're pumping additional y's into w. Okay, so you have wi, that must belong into L. So any amount of y's you inject into w, the resulting string is going to have to be in L. Okay, so this was the pumping lemma. We proved this on Tuesday at the end of class. There's also, I'd like to point out, because someone asked this, there's an extra handout under lecture 10, where, so this isn't quite the most formal way of stating the pumping lemma. There's a way of doing it using sort of predicate and propositional logic, but that sort of becomes like complete, very sort of archaic and gibberishy kind of notation. But it does help to see what exactly is going on. So I'll just say there's an extra handout where the formal pumping lemma, well, the pumping lemma is written down using propositional logic, using predicate and propositional logic. And the reason why I point this out is because now we're going to have to negate or take the contrapositive of this statement. And to take the contrapositive, you have to negate this statement and this statement. Well, this statement is super easy to negate, right? L is regular. The negation of that is L is not regular. But this statement, not so obvious, right? But if you see it in terms of propositional logic, then it's just some mechanical procedure. Right? But I'm going to sort of skip the mechanical procedure, and I'm just going to give you sort of the highlights of what happens when you negate the statement. Okay, so let's take the contrapositive. So let's take the contrapositive by negating. So let's say this is statement 1, and this is statement 2, by negating 1 and 2. Okay, so I have if 1, then 2, and now the contrapositive, which is logically equivalent to the implication, is not 2, then not 1. Okay. So I need to negate the statement here. Well, to negate the statement, I know that I have a bunch of quantifiers. I have existential quantifiers and universal quantifiers. And so the only thing I'm really going to do is I'm just going to use this thing, this property that hopefully you've already seen, that when you negate, say, an existential quantifier, and you have some statement P of X, so you know there exists some P of X for which, there exists some X for which P of X. If you negate this, then this becomes for every X, not P of X. And the same thing for the universal quantifier. So if you have for every X, P of X, and you negate this, then you get there exists an X for which not P of X. So that's all I'm going to do. I'm just going to do this sort of, I'm going to apply this to each of these lines. Okay, so let's do that. So the first line is there exists a P in the set of natural numbers that is strictly positive. So I'm going to negate that. So the negation is going to be, let's put this on right. So the negation is going to be for every natural number, which is strictly greater than 0. Okay, so I negate that first line, then I negate the second line. The second line is negated. So you take the for all and you make that in there exists. So there exists a string W and L for which the length of W is greater or equal to P. And then the third line here is a there exists again. So if you negate that, that's a for all. So you get for all, for every possible decomposition of that string, where that string satisfies the property that xy is at most P, the length of xy that is, and the length of y is strictly greater than 0. Then if you negate the last statement here, the for all becomes that there exists. So there exists an I in the set of natural numbers for which Wi xyi z is not in L. Okay. So this is the negated version of the conclusion of the pumping lemma. Okay, so one thing that you might be asking yourself is, well, according to this logic here, why am I not, say, negating this, right? Why am I not negating this statement? So the reason for this is it kind of has to do with looking at the statement slightly more formally in terms of propositional and predicate calculus. But the general idea is that these things are in the sort of conditional of an implication. And so when you negate an implication, the premise of the implication doesn't become negated. It just becomes conjoined with the negation of the conclusion. So all I'm doing is I'm just applying. So all I'm doing is I'm just taking if P then Q. and I'm negating that, and that is, it turns out that is equivalent to P and not Q. So I'm just sort of applying this logic to this larger statement. So that's why this is the only thing that actually got negated. Okay. Okay. Right. So, well, this doesn't seem very helpful. How can we actually use this? Because now I've said, you know, I've shown what the contrapositive is. It's if this is true, then L is not regular. L is not regular. So how can I actually use this? Well, what we're going to do is we're going to play a game. So maybe this game is going to wake you up because you seem very sleepy. Okay. So using the pumping lemma to prove non-regularity by playing a game. Okay, so what does this game look like? Essentially, what you want to do is you want to make the statement true, right? And so to do this, what you're going to do is you're going to play the existential quantifier. So you're the there exists, and you're going to play against an opponent. The opponent is the for all. Okay, so it starts by your opponent picking some natural number p. Okay, and then your opponent plays. The opponent has to respect the rules, so you know that p is strictly greater than 0. Then it's your turn, right? It's your turn to play. So at your turn, you have to pick a particular string w where the length of w is greater or equal to p. So that's your move. Then it goes back to your opponent. The opponent is the universal quantifier. So the opponent is going to decompose the string, and they decompose the string in a manner that respects these rules. Okay. But remember, you're playing a game, right? And so this is like a classic game like chess. You can't sort of control your opponent's move, right? So you have no control on what the opponent picks in terms of p and what the opponent picks in terms of the decomposition. Your strategy has to work for whatever p and for whatever decomposition. Okay. So once you say, okay, well, I know roughly what the decomposition could be, because I'm sort of keeping track of all the possibilities of what my opponent could do, then I have to pick some I. I have to pick some I for which I get that wi, xy, iz is not in L. Right? And that's how I defeat my opponent. So the goal of the game, right, is of course to win. So the goal of this game is winning, right? Why would you play a game otherwise? And so you play the existential quantifier, and your opponent plays the universal quantifier. Okay. And just a side note, I'm going to say opponent because I think that's slightly more friendly. What Prakash used to do, well, no, what Prakash does is that instead of calling it the opponent, Prakash calls it the demon. But that sounds a bit scary. Why would you want to play against a demon? That's no fun. So it's just some opponent, right? Okay. Because otherwise it doesn't seem, I don't know, I couldn't defeat a demon if I tried. Okay. So this is the general idea. Now, at this point, this might seem a bit abstract, because it is. So to unabstract it, let's look at an example. So the example is going to be to prove, using the pumping lemma, that the language L, which is A n Bn, so we already proved that this is non-regular. So by the time we're done, it's going to be doubly non-regular. But we're going to show using the pumping lemma that this is not regular. Okay. So before I start this example, are there any questions? No, it doesn't look like it. Okay, good. Okay. So I want to use the pumping lemma to show that this language is not regular. So how am I going to do this? Again, I'm going to play a game, right? So the game starts with my opponent, the for all, who picks some natural number p. So let's just say that my opponent picks some natural number p, which is positive. Okay, I don't know what it is. I have no control over my opponent. Now the existential quantifier, which is me. Now what I need to do is I need to pick a string that has length at least w, but it actually has to have a few more properties than that, because I have to sort of think a few steps ahead. I have to think based on whatever my opponent does, based on whatever decomposition they take. I need to be able to find an I. So in 2 steps from now, I need to be able to find an I such that when I pump it, so when I create the string X, Y, I, Z, I get a string which isn't in L. Okay, so this is sort of the setup, the mind space you need to be in to sort of pick the correct string W, or a correct string W. There's many correct strings. Okay, so in this case, a successful string is going to be the following: AP, BP. Okay, which, even if you didn't really understand the argument about thinking 2 steps ahead, kind of makes sense, right? It has to be, this string has to be an L. So it has to have an equal number of A's and B's. And it has to have length at least P. Well, in this case, I have length 2P. So that's clearly greater or equal to P. So the length of W here is 2P, which is greater or equal to P. Okay, so this is a legal move, right? Now it's the turn of my opponent. So the for all player. So the opponent is going to decompose the string. So my opponent decomposes W into XYZ. But remember, the opponent has to follow the rules of the game. Otherwise, they're disqualified and sort of I win automatically. So they have to follow the rules that XY, the length of XY has to be at most P. And the length of Y has to be strictly greater than 0. Well, I know that I said at the beginning that I can't control what my opponent does, but I can sort of foresee what they'll do. Because in this case, there's sort of a limited number of possibilities. Because I know that W is a sequence of A's, and then a sequence of B's. Okay. Well, how many A's do I have? I have PA's. So I have PA's. And how many B's do I have? I have PB's. And what do I know? I know that my opponent has to decompose the string such that the decomposition is XYZ, and XY is within the first P letters. So what does that mean effectively? That means that XY has to be in the bunch of A's, right? Because the length of XY is at most P. So the XYs can't go past the last A because I have PA's, right? If the XY went past the number of A's, then the length of XY would be P plus 1, which then that means my opponent isn't following the rules, and that's very bad. Okay. So I know that XY has to be within the A's, and then the Z, it doesn't really matter, right? So maybe my opponent picks this as the block for XY. Let's make a proper block here. This is XY. And then they make another block just for Z. Okay, so this is Z. Doesn't matter what Z is, right? Maybe it's, the A's and then the rest of the B's. Maybe it's just the B's. The only thing I really care about is what the Y is, really. Why do I care about what the Y is? Because I'm going to have to pump it, right? That's what's going to determine whether the I picked is successful. Okay, so what I know then is that because XY, the decomposition or the substring XY is within the A's, I know that Y is just a sequence of A's, right? So I know, so I haven't played the there exists move yet, but this is sort of, I'm thinking about what I should play in my move. And so I know that the string Y is just a sequence of A's, right? In particular, let's just say that they're KA's, right? Where K has to be at least 1, okay? Because the cycle has to be non-empty. And it's at most P. Because the length of XY is at most P, X could be empty, so then Y could be of length at most P. Okay. So I know this, and this is going to help me out when it comes back to my turn, which is right now. Okay. So at this point, I need to pick. So what do I need to do? I need to pick an I such that WI X, Y, I, Z is not in L. Okay. So it turns out here, whatever you pick, right? as long as it's not 1, because if you pick 1, then if I is equal to 1, then you have XYZ. Well, XYZ is this string. So of course it's an L, right? That's the string you picked. That was an L to begin with. So it turns out whatever I you pick in this case, it's going to work out. You're going to get that the string, the pumped string, is not an L. So in particular, let's just say I pick I is equal to 2. If I pick I is equal to 2, what happens? Well, to make this super explicit, let me just rewrite. Let me copy this over. Copy, paste. Okay, very good. Oh, okay. So I have my string W. And now let's make things slightly more explicit. Let's sort of make it clear how this delineation is occurring in terms of the substring. So let's say this is X, this is Y, and this is Z. Okay. So what happens if I pick I is equal to 2? If I pick I is equal to 2, that means that W2 is X, Y2, Z. Right. Well, what is X, Y2, Z? It's just X, Y, Y, Z. So what's going on is I take this original string. So this is my original string. This is W1. Okay. This is my original string. And what I'm doing is I'm pumping up, right? I'm pumping up because I'm taking this Y and I'm injecting an extra copy. Right? So you can just think of this as saying, let's take this Y and let's inject an extra copy in here. Okay, so then what happens? What happens is then I get the string W2. The string W2 is, the initial X, the initial Y, the added Y, and then the rest of the string Z. Okay. Okay, well, what does this mean? This means that I know that to begin with, I had PAs, right? Remember in here, I had PAs. But now what's going on is I'm injecting an extra string Y into the A's, into the sequence of A's. And I know that Y has KAs, right? So what that means is that as a result, in terms of number of A's, I have the initial number of A's, which was P, plus K. So I have A power P plus K in terms of number of A's, and the number of B's stay the same. Okay. And clearly this is not an L. This is not an L. Why is this not an L? Because remember the definition of L is the language over the alphabet AB, for which the number of A's is equal to the number of B's, and you have a sequence of A's and B's, right? But of course, this doesn't satisfy this definition. Why? Because P plus K is at least P plus 1, because I know that K is at least 1, right? I know that the length of the cycle is at least 1. It's not empty. And P plus 1 is strictly greater than P, right? So of course, P plus K is not equal to P because 1 is strictly greater than the other. Okay. So as a result, by the pumping lemma, L is not regular. Okay, so essentially what we've done is we've proved now twice that AN BN is not regular. Any questions about this? No questions? Really? Okay. Yeah. Oh, okay. So in which part do we use the pumping lemma? Well, essentially, right. So essentially, all of what I've just done here, so everything I just did here, this is all the negated conclusion of the pumping lemma. Okay, so I have if P then Q. So what I've just shown, I've shown that not Q is true. And so by contrapositive, that means that not P is true. But not P is L is not regular. Yeah. So everything together, so doing all of this process together shows that this statement is true, but this statement is the negation of the conclusion of the pumping lemma. So by contrapositive, that means that L is not regular. Good, okay, good. I'm happy that it's good. Anthony, you have a question? No? Okay, all right. So there are no other questions. Let's do another example. This example is actually going to be quite neat So it's actually going to leverage the closure properties, which we saw in lecture 6, but are actually quite useful when you want to prove non-regularity. Okay, so the closure properties can be helpful in proving non-regularity. Okay, well, how can it be helpful? What do I mean exactly? So let's take the following example. Suppose that I want to show that the following language is not regular, where this language is the set of all strings of the alphabet for which those strings have an equal number of A's and B's, right? So the number of A's and B's is exactly the same. So this is kind of like A and Bn, right? In A and Bn, you have an equal number of A's and B's, but there's an additional restriction that the A's start the sequence of strings and the B's finish off the sequence of strings, right? So I could sort of start a pumping lemma proof from scratch, but actually I don't need to. Why? Because let's just suppose for an instance, suppose for contradiction, that L is regular. Okay, so I know that L is regular. I'm just supposing this. Now, what do I know about regular languages? I know that regular languages are closed under the intersection. So if I take L, right, remember L is just the set of all strings for which those strings have an equal number of A's and B's. And now I take the intersection with the following regular language, A star, B star. Well, why is this language regular? There's a regular expression that's right there that describes it. So this language is regular. This language is regular. This language is regular by assumption. So regular by assumption. And so by the closure properties, I know that the resulting language must also be regular. But what is the resulting language? Well, you have to think of the intersection, right? So what does the intersection mean? For a string to be in this intersection, it has to be both in L and in A star, B star. So for the string to be in A star, B star, it has to have a sequence of A's and then a sequence of B's, right? By the intersection. But then if it's also going to be in L, it has to have an equal number of A's and B's. Well, what I've just described, I've sort of just described what A and Bn is, right? Just described A and Bn. Okay. But now by the closure properties, what I've concluded that this language is regular. Well, that's clearly a contradiction because I know that A and Bn is not regular. It's doubly not regular. I've proved this twice. So this is a contradiction. This is my symbol for contradiction. So that means that my initial assumption was incorrect, and therefore L cannot be regular. So that shows that this language is not regular. Okay. Let's do another example with closure properties. This one is slightly more tricky, but not really all that much trickier. So I want to show, let me not write the instruction because that's a waste of time. I just want to show that A and Bm, where in this case, N and M are natural numbers, but N is not equal to M, right? So in this case, I have a sequence of A's and then the sequence of B's, but now I'm saying that the number of A's has to be different from the number of B's, okay? Okay, so there's a few ways you could show that this is not regular. So the first way could be using the Myhill-Néraud theorem. This would be not that hard, actually. It'd be like maybe one, I'll get to you in a second. This would be like maybe a paragraph, not too bad. Then you could use the pumping lemma. The pumping lemma proof is actually pretty tricky because it's hard to find a suitable W. I'll leave this as an exercise. But as a hint, when you pick W, you need to use a factorial. Okay, so if you work it out, if you try a bit, you'll see why you need a factorial. But it's not a super intuitive or like, you have to be like really, really clever and you have to sort of If you haven't seen the example, then it's really hard to think about it. It takes you like 2-3 hours to do it. So, that's probably not super promising. So instead, what I'm going to do is I'm going to use the closure properties again. Okay, so how am I going to do this? Let's assume that L is regular. Right, so for the purposes of the contradiction, I'm assuming that this language L is regular. Now let's consider the following resulting language from language operations. You take the language L and you take its complement. Okay, so the language L complement, well, that's all the strings, I'll get to you in a second. All the strings L, all the strings that are not in L, right? So, well, I have to consider what are the strings that are initially in L? What are the strings that are initially in L, right? Those strings that are initially in L are strings that start with A's, end with B's, and the number of A's and B's are different. So the complement is everything but that. Right? So in particular, that includes strings which just don't follow this pattern, right? So for instance, you could have B, B, A, B, A. This would be an L complement. Why is it an L complement? Because it just doesn't have this pattern. The other types of strings that are in L complement are the strings where they do have this pattern, but the number of A's is equal to the number of B's, right? So in other words, you have, say, A3, B3 is also in L complement. So what you're going to do, you're going to use the intersection again. You're going to use the intersection to filter out all of these strings. You don't want these strings, and you're just going to want to preserve A and Bn, right? That's the goal, really. The goal behind this sort of closure property trick is you assume that L is regular, and you sort of apply these properties, these language operators, which regular languages are closed under, to get to a language which is not regular. So that's what I'm going to do again in this case. In this case, I'm going to intersect with the same language as before, A star, B star. And this is going to give me, again, AN, BN, for N is some natural number. Right, but the conclusion is, because L is regular, I assumed it was regular, L complement is also regular because regular languages are closed under the complement. So I have that this language is regular. Then I have that this language is regular. Or why is this regular? I have a regular expression that describes it. So of course it's regular. And then I know that the intersection, that regular languages are closed under the intersection, which means that the whole combined language is regular, which means that this language is regular. But again, that's a contradiction because I've shown this twice, that A and BN is not regular. Okay. So that's how you could do that. Arthur, you had a question?
In an example, you use the closure properties to prove the language is not regular.
Yep.
The fact that A and
Yep.
is not regular.
Yes. No, you can assume. Yeah. Nicholas. Yeah. So remember, A star, B star, that's a regular expression, right? And then if you take L of a regular expression, it returns the language described by that regular expression, right? So A star, B star matches any string which has a number of A's followed by a number of B's, any number, right? And so the return language is the language containing strings with a sequence of A's and a sequence of B's, where there's no restriction on the number of A's and B's. Okay. Good. Okay, excellent. So far in the examples we've seen, oh yeah, Marcello. Yeah.
Okay. The pumping lemma.
Yeah.
It's like the pumping lemma that wasn't created like incidentally to some other proof that it has having to.
No, this is what I'm saying on Tuesday. It should really be called the pumping theorem. Yeah. Well, I guess it's a lemma because you're proving, the theorem that, say, some language is not regular. Yeah. Okay. Wow, I can see you so much better. Okay. So what I'd like to point out so far, right, is that so far what we've done, right, we've looked at languages. So we've looked at, really just 2 or 3. But all of these languages, you could use the Myhelner road pretty easily to show that the language was not regular, right? So what's the point? Why am I using the pumping lemma? Well, it turns out that sometimes it's actually quite difficult to create the set S for the Myhill-Nerode sort of proof technique to show that a language is not regular, but it's relatively easy to do so using the pumping lemma. So it's relatively easy to do a pumping lemma proof than it is to do a Myhill-Nerode proof. So that's sometimes true, and other times it's easier to do a sort of Myhill-Nerode type proof. So let me just write what I just said. So we know that Myhill-Nerode can be used to prove non-regularity, but sometimes it's not so easy to find S, right? Because remember, S on Tuesday, that was the set of strings which would individually create, for which each of the strings in the set S would create distinct equivalence classes, showing that the index of the Myhill-Nerode relation was infinite. Sometimes that's not so easy to find. So what's an example of a case where that's not so easy to find? Well, let me show you one. So suppose I have the following language, L, which is a(n) square. So it's a number of a's where the number of a's is a perfect square, where n is a natural number. So what I'd like to do is I'd like to show that this language is not regular. Okay, so intuitively, why is this not regular? Because there's an infinite number of squares, right? And so what a DFA would need to do, to accept a language L is it would sort of have to memorize every possible square, right? But there's an infinite number of squares, and so the DFA would need to be infinite, which we know is not possible. So if you wanted to use the Myhill-Nerode theorem, it would be quite tricky to find an S. So one possible one would be the following. I'll let you work out why. Okay, this would be one possible set S that you could use to then show that the language is not regular using the Myhill-Nerode theorem. But this is not so obvious, right? You have to sort of think about sort of a nifty little basic number theory property, or really just a basic number of a basic property of numbers. So that's not so easy. The easier proof is really the pumping lemma proof, okay? Because I'll show you in a second, it's really not that bad. Okay? So let's do another pumping lemma proof. So let's use the pumping lemma to show that this language L is not regular. So again, remember what I'm going to do is I'm going to play a game. I'm going to play a game where the game is to show that the negation of the conclusion of the pumping lemma is true. Okay, so how does this game start? It starts with the universal quantifier. So the opponent is going to pick. So the opponent picks some natural number n, or some natural number p, where p is positive. Okay, so I have no control over what p is, right? P could be a perfect square, or it could also not be a perfect square. I have no idea what my opponent picked, right? So now for my move, right? For my move, what I need to do is I need to pick a string which is in the language L. So in other words, I need to pick a string where I have a's, where the number of a's is a perfect square. Okay. Well, an easy way to do this, an easy way to create a number of a's with a perfect square as the number of a's would be the following. If I create the string w is a p squared, right? Of course, that's a perfect square because I've just taken a number and I've squared it. So clearly that's going to give me a perfect square, right? And the other thing, so I know this is an L. And because we're dealing with positive natural numbers, I know that p squared is greater or equal to p, which is the other sort of rule that I need to respect to play this game. Okay. So now the move goes back to my opponent. So now it's the universal quantifier that plays. They have to decompose the string. The string W is just a bunch of A's in this case. Right, it's just a bunch of A's. In particular, I have P square A's. So I know that when my opponent decomposes the string, they'll decompose it as such. Right? But in this case, they have no choice as to what Y should be. Y is clearly just going to be some number of A's. Right? So clearly, it must be that y is some number of a's, let's say k a's. And because I know that my opponent has to respect the rules, the opponent has to respect the rule that the length of xy is at most p, and the length of y is strictly greater than 0. So then k has to be strictly greater than 0. In other words, it has to be greater or equal to 1. And k has to be at most p. Okay, because my opponent is respecting the rules, so the way they decompose the string has to look like something like this. Okay. So now it's back to my turn. It's back to my turn. Now this is not as obvious, I'd say, as the first proof with a and bn. So you have to be slightly more crafty in this case. So the choice of I is going to be relatively easy, but the argument for why the string, the pumped string, is not L is going to be a bit more, is going to require a bit more work. Okay, so what do I mean by that? Well, let's do the same thing I did before. Let's take my initial string W. Let's put it here. Okay. So I know that this is W1, right? So this is X, Y1, Z. Right? So then what would be Wi? In general, what would Wi be? It would be taking the string W1 and adding Y's I number of times, right? So it would be, you take the X and then you add Y I number of times. Then you add Z. Okay. So in general, how can I represent this? How can I represent Wi? Well, I know that XYZ is a P square, right? So then Wi is just going to be taking the Y, right? So I have KAs in the Y and pumping that up I times. So that means that Wi, or Wi, sorry, is going to be A P square plus IK. So this is wrong, actually. So I've made a mistake. So this is not quite right. Why is this not quite right? Yeah. 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 Well, not K minus 1. I minus 1. Yeah. Yeah. Right. Very good. So this is not quite right. This is not quite right. And the reason why I point this out is because this is a common error. So this is a very common error that students make. So be on the lookout for this. So this is a common error. It's not P squared plus IK, because when I is equal to 1, it should be AP squared, right? But if I is equal to 1 in this case, then I have P squared plus K, right? And that's not the initial string I had, okay? So really what I should write, is A P squared plus I minus 1, okay? Okay, good, all right. So now, what happens if, say, I pick I is equal to 2? If I get I is equal to 2, if I pick I is equal to 2, then W2 is, by the construction I just gave here, it's going to be A P squared plus 2 minus 1 times K, which is A P squared plus K. So now it turns out that this choice was actually pretty good, because it turns out that this is not an L. But in an assignment solution or in a midterm or in a final, you can't just write this, because this isn't all that clear to me. Like at this point, you still have to argue a bit more that this is not an L. So in other words, you have to argue that P squared plus K is not a perfect square. So how can you argue that? So this is a common trick actually in sort of a pumping lemma proof, when you're trying to argue that a particular number isn't, a perfect square, factorial, or a cubic number. So it's a common trick that you do here is the following. You say, take P squared plus K. This is my sort of natural number line. So P squared plus K is a natural number. What I'm going to do is I'm going to show that P squared plus K is in between two consecutive perfect squares. So I'm going to show that P squared plus K is in between P squared and P plus 1 squared. So if I show that P squared plus K is strictly greater than P squared, and it's strictly less than P plus 1 squared, then because there are no other perfect squares in between, p squared plus k must not be a perfect square. So that's all I need to argue now. I just need to show that, that this is true and that this is true. Well, this first inequality is not too bad to show because I know that k is greater or equal to 1. I know that k is greater or equal to 1. So that means that p squared plus k is greater or equal to p squared plus 1. And the p squared plus 1, you're adding 1 to some number. So of course, that's greater than the initial number, strictly greater than the initial number. So that's strictly greater than p squared. So that shows this inequality. So it shows that p squared plus k is strictly greater than p squared. So what about the other side? The other side here is equally as easy, I would say. But you just have to notice something. You have to notice that k is also upper bounded. K is upper bounded by p. So if k is upper bounded by p, then I know that p squared plus k is less than or equal to p squared plus p, right? Because k is less than or equal to p. And then this is less than or equal to p squared plus 2p, which is strictly less than p squared plus 2p plus 1, right? Why do I have strict inequality here? Because I'm adding a plus 1 here. So of course, if I have, some number and some number, but I add plus 1 to it, then it must be strictly greater than the initial number. Yes, so strictly speaking, this could also be a strict inequality, but because p has to be strictly greater than 0, but this argument is good enough. Yeah, but thanks for the comment. Okay, so then I know that p squared plus k is in between and not equal to p squared and p plus 1 squared. So because I know that I have sort of two consecutive squares, there aren't any perfect squares in between those consecutive squares, right? Because they're consecutive. Right? And so that means, so therefore, p squared plus k is not a perfect square. So this sort of completes the proof that the negated conclusion of the conclusion of the pumping lemma is negated. So by contrapositive, this shows using the pumping lemma. So by the pumping lemma, L is not regular. Okay. Any questions about this? Okay, so let's do another one. Let's do another exercise. In this case, it's not going to be use the pumping lemma to prove something. It's going to be slightly harder. Okay, so I have this language L, which is a sequence of A's and then a sequence of B's, where there's a few sort of necessary and sufficient properties that force a string to be an L, that make it such that a string is an L. In particular, the number of A's cubed has to be equal to the number of B's. Right? And this number of A's here has to be even. So now the question is L regular? If yes, design an FA. If no, use the pumping lemma to prove your answer. So let me venture a question. Is this regular? Anyone else but Owen? Anthony? No, why is it not regular? Yeah, good, right. So no, this is not regular, no? Because let's sort of quickly suppose that I wanted to create a DFA that accepted this language. Well, I would need to remember how many A's I've seen so that I can check that the number of A's cubed is equal to the number of B's, okay? But because I have an unbounded number of A's, then the DFA that would result from this creation, from this construction, would be infinite. And of course, I can't have an infinite DFA. So the answer is no, okay? So let's use the pumping lemma again. So this time I'm gonna go a bit faster because now I've shown you two examples. So you're experts in the pumping lemma now. So again, let me start with my opponent picking some natural number. So I pick some natural number p, which is strictly positive. Okay. So now I have to pick a string, right? I have to pick a string which is an L and which has length at least p. Let's see. So how about I pick this string? Is this good? Ben?
No, he's not necessarily.
Very good. So this is not good. Very good. Thank you, Ben. This is not good because P is not necessarily even, right? A very important point to remember, right? You have no control over what your opponent picks. You just know that they picked some natural number. So very good. So that's not going to work. Okay, well, how do I force an integer to be even? I'll multiply by 2. Right? Then it's going to be even. So let's say I pick a 2p, b pq. What about this? Is this good? Why is this not good? Marcello?
Because it has to be.
Right. So this is not good because, well, now, yes, the number of a's is even, but p cube is not equal, or 2p cube is not equal to p cube, right? Because the number of b's has to equal the number of a's cubed. Okay, well, I think we're almost there. We're almost at a correct string. If I pick w is a 2p, b 2p whole cube, I think that works out, right? We're happy with this. Okay, so this is good. Little smiley face. Excellent. So now it's back to my opponent's turn. My opponent decomposes the string, right? So they decompose the string. I'm not going to sort of rewrite it. I'm just going to say they decompose the string w into xyz. So what must y equal, right? So w is a sequence of a's and then a sequence of b's, and w, the first part of w is 2pa's. Yes?
The second one.
Oh,
Like the one on A. And the one.
this one?
Yeah.
Because here, right, here what this is saying is that if I have some number of a's, right, and I cube that, right, so I cube the number of a's, then that should be in the number of b's, right? But this is not what I have here, right? Because I have the number of a's, that's 2p, and I cube that, but that's not the number of b's I have here. Okay, because 2p cubed is strictly greater than p cubed, for p is a natural number and positive. Maybe we can talk about it offline if you want. Yeah, I'd be happy to answer in more detail. Okay. So my opponent decomposes the string. The string has to be xyz, where xy is the first is within the first p letters. So what does y have to be? Yes, Lothar. Very good. So can you give me a name to that sequence, the number of a's? Very good. Excellent. Very, very good. And less than p. Very good. Excellent. I didn't even ask for the less than p. Thanks very much. Excellent. Okay. So I know that y is a power k, so I have ka's. Now it's back to my turn. Right? It's back to my turn. I need to pick an I. So far I've been pumping up. Let's try something different. Let's pump down. So let's pump down. So pumping down is when I pick I is equal to 0. When I pick I is equal to 0, I get that W0 is xz, right? So I've sort of removed the y. I've pumped down, so I've sort of eliminated the y from my string. So now my string W0 is going to be, well, I know it's some number of a's. I initially had 2pa's. And some number of b's, I had 2p whole cube b's. But now what happens to my number of a's? Come on, Arthur. Take k away. Excellent, very good. Thank you, Arthur. So 2p minus k. Very, very good. Excellent. And this is clearly not an L. Right? Why is it clearly not an L? Because 2p minus k is strictly less than, or not. No, is less than or equal to 2p minus 1 whole cube, sorry. Right. And this is strictly less than 2p whole cube. Because I'm taking some number and I'm removing a 1 from it. So, and I'm cubing it, and I'm dealing with sort of natural numbers. So taking a number, then taking away one and cubing it is strictly less than taking a number and cubing it. If you're dealing with, p is a natural number and positive. Okay. So then that means that the number of b's here, the number of b's is not equal to the cube of the number of a's. Right? And so by definition of what L is, that means that W0 is not an L. So I found an I for which I get a string which is not an L. And so again, by the pumping lemma, L is not regular. Good. Questions about this? No? Okay, good. Good. I have time for two more examples. Did I say 9:45? I meant 9:47. No. 9:45 is good. Okay. So let's do another one where I ask you if the language is regular. So suppose I have the following language L. I have AN BM, where N mod 2 is equal to M mod 2, where N and M are, of course, natural numbers. So now the question is L regular? Is it regular? I mean, I'm saying that the number of A's and B's have to be the same, but mod 2. So does that make it regular or does that make it not regular? Yeah. But you're saying it's not regular or it is regular? But you can have an infinite number of A's, but really the only thing you need to keep track of is the parity, right? So the parity, that's just sort of 2 bits of information, right? You have a state which encodes, you have an even number of A's and a state which encodes an odd number of A's, right? And so it turns out that the answer here is yes, it is regular. Okay.
What's the difference in this question on a different view?
I'm perplexed by this question. I'm gonna ignore this. No. Okay. What was I saying? Damn it, Marcello. Yes, it is regular. It is regular because the states your DFA is going to have are going to encode sort of finite pieces of you only need a finite amount of memory to sort of accept strings in this language. Why? Because really what you need to do, the only thing you really need to do is you need to check that N mod 2 is equal to M mod 2 is equal to 0. So they're both equal to 0 or they're both equal to 1. Well, I know how to check that the parity of the number of A's is, even or odd. And I know how to check that the parity of the number of B's is even or odd. So, you can imagine just creating an FA, which has 2 branches. The first branch is you guess that the number of A's mod 2 is equal to the number of B's mod 2 is equal to 0. So you have one branch, which is that guess, and another branch, which is the guess for it's equal to 1, right? So, you have your start state, then you have a branch which checks the parity of A's, another part of the branch which checks the parity of the B's, of the number of B's, and then you can do the same thing for the number of A's and the number of B's for the other branch. Okay, and so one branch is going to be when N mod 2 is equal to 0, and another one is going to be when M mod 2 is equal to 1. Okay, so clearly I can create a DFA which accepts this language. Okay, so now an exercise for you. So what if I remove the modulo 2 from one of the 2 integers? So what if I say the language L, which is ANBM, where N is equal to M mod 2, and N and M are natural numbers. Okay, so I'll leave this for you. So this wasn't on a midterm. Okay. I don't have time to do this one, but I'll also leave it as an exercise because it's a quite nice exercise. So in this exercise, the question is which of the following? This is also going to be, there's going to be a similar question on your assignment. So which of the following languages are regular? And I have the following 3 languages, which all look fairly similar. So they're all sequences of A's and then sequences of B's. But there's some restrictions on the number of A's and B's, of course. So these are the restrictions. For the first one, n is strictly less than m is less than or equal to 330. Why 330? I'll let you guess why. The other one is that n is strictly less than or equal to 330, which is strictly less than m. And the last one is 330 is strictly less than n, or less than or equal to n, and n is strictly less than m. Boy, I should have just written it down. I shouldn't have said it, but anyways. So this is an exercise for you, a very nice exercise, which I don't have time to do. The last thing I want to do though, is I want to show you something interesting. And this interesting thing has to do with closure properties, because so far, when discussing, let's say, language operators applied to regular languages, we've seen that these language operators preserve regularity, right? So we've seen they all preserve regularity. So in your assignment 2, you have 2 language operators which preserve regularity. In lecture 6, we saw that the union, the intersection, the complement, the star, all those operations preserve regularity. So you might be thinking, are there language operators which don't preserve regularity? So that's exactly what I'm going to talk about. So they all preserve regularity. So now let's consider the following. Let's consider the following language operator. Okay. So I need to give you a bit of setup before I give you the language operator. So imagine, in this case, the alphabet is 0, 1. And I'm going to inject some order into my alphabet. I'm going to say that 0 is strictly less than 1. Okay, so there's an order in the letters. And now, suppose I have some string x in sigma star. So in this case, x is a sequence of 0s and 1s. And consider the following operator, sort of x, which I'm not going to define it recursively. That would be super annoying. But what it does is it rearranges x such that the letters in x are sorted, right? So that's exactly why it's called sort. So for instance, if I take sort and I apply this to 1, 0, 1, 0, 0, then what happens is I take all the zeros and I put them at the beginning, right? So I get 0, 0, 0, and then I put the ones at the end. 1, 1. Okay. So now I'm going to ask this as a true or false, but I've kind of sort of given the answer to the true or false already. But it's the counter example that's actually interesting. So true or false, if L is regular, then so is sort of L, where sort of L is take each string in L and sort it. Okay, well, I mean, I kind of sort of premised the whole example with the fact that there are some language operators which don't preserve regularity. So in fact, this is false. But the actual interesting thing is the counterexample, which I'd like you to think about. What is a counterexample to show that sort of L does not preserve regularity? I'm gonna actually make you think about it. No, let's give everyone some time to think about it. Wait, do like 15 more seconds. Okay. Any ideas on a counterexample? I'd like to ask someone who hasn't spoken before. I'd like you to spit the toad. Yeah. Well, let's talk about the letters 0, 1. Excellent. Very, very good. Oh, excellent. Great. Right on time. Very good. Excellent. Very good. So a counterexample would be if you take the language L, which is 0, 1 star, right? Well, what is this language? This language is strings with a sequence of 0, 1s, right? So it has, 0, 1, 0, 1, 0, 1, 0, 1, and so on, right? And so what you'll notice is that by construction, the number of zeros and the number of ones are equal, right? So for every 0 you also have a 1, right? And so what happens when you sort, let's say 0, 1, 0, 1, 0, 1, well, you take all these zeros and you put them at the front, and you take all the ones and you put them at the back. And so then what you can show, it's not that hard to show, is that sort L of 0, 1 whole star, that's equal to 0n, 1n for n is a natural number. And of course, this is clearly not regular because it's exactly the same as an, bn. Okay. So there's a similar exercise like this in your assignment. Good. Okay, let's talk about the midterm. Are there any questions about this? No? Okay. All right, so let's talk about the midterm. So there's a midterm. I don't know if you're up to date on things, but it's October 13th, which is a terrible date to have a test, the 13th of October. Well, in Italian culture, that's actually lucky. So what? Oh. Oh, I see. But in Italian culture, this is lucky. So you'll be okay. Okay. So it's at so it starts at 6:05 p.m. and strictly speaking, you have 80 minutes. If you need more time, I'm not a monster. Maybe I'll give you more time. I don't think you'll need more time, but I think 80 minutes is more than enough. The other thing is that there's 2 classrooms where you'll be sitting. Well, you won't be sitting in both of them at the same time. That would be impossible unless you're living in the quantum world. But there's 2 classrooms for the midterm. So there's I think there's one in Leacock. I think it's 219. And of course, the other one is not anywhere close to Leacock. It's in Adams. It's in the Adams Auditorium, which are both, by the way, terrible places to write a midterm. So I don't know. I could ask, but I don't think I'll have the time to complain. So I'm going to send you an email. I'll send an email, or I'll send an ed. I'll post something on ed. Come on. I'll post an ed announcement. Ed announcement for who goes where. Okay, so don't worry about that. The other thing is, please bring a piece of ID so that I can verify that you're truly writing your own midterm and you're not some genius who took it 3 years ago and got an A and is just sort of rewriting it for a friend. So please bring a piece of ID, a driver's license or your student ID. That's good enough. And the other thing is that you will be allowed a 1-page cheat sheet. Well, you didn't know about that? Okay. So you have a 1-page cheat sheet. The restriction on the cheat sheet is that it has to be 12 point. So 12 point times New Roman. And so, I'm not gonna, inspect each cheat sheet extremely carefully, but this is an example of what I mean by 12 point and not 12 point. So this is 12 point. This is 12 point. And then this is not 12 point. Okay. So don't do that. This question? No, don't type it. It has to be handwritten. 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 Okay, what is this with the Arthur, yeah?
One-sided or?
One-sided, one page, one-sided, one side. One side. Handwritten, one side. And if you don't think I'm gonna check it, oh. I will check. Okay? Prakash didn't check because what does he care? But I will, okay? Okay, good. So that's all the admin stuff about it. And so the actual thing you probably want to know about the midterm is, what's on it. So there's 5 questions. There's 5 questions. 1, 2, 3, 4, 5. What? The fifth one is a true or false. So there's 5 true false questions, which are about contents from lecture 2 all the way to lecture 11. So today's lecture. Then the other questions are sort of long answer questions. So the first one is going to be about designing an FA. So in particular, there's like a few types of questions I might ask. The first one might be, design a DFA and then make sure it's minimal. I'm not going to ask you to prove correctness, obviously, that would be crazy. The other thing I could ask is, make an NFA, make sure to use non-determinism, right? Use non-determinism, like I asked you in assignment 1. Or, make sure you use an NFA with epsilon transitions. Okay. Then the second question is going to be about writing regular expressions. There's going to be 4 languages. So it's an ABCD question, where the languages get slightly more, what's the word? Tricky. They're not really tricky. None of the questions are tricky. Okay, but the first question is worth 1 point, which means it's pretty easy. And then the last one is worth 4. Okay. Oh, each question is worth 10 points. So each one is worth 10 for a grand total of 50. I hate it when professors, they say, oh, the midterm is worth 20, so let's make the midterm out of 20. Doesn't make any sense. Okay, sorry. So that's question 2. Question 3 is I will ask you to use the Myhill-Nerode or the pumping lemma. I'll state which one you have to use to prove that a language is not regular, to prove non-regularity. And the last one is I'll ask you decide whether L is regular. Okay. If it's regular, design an FA for it. If it's not regular, do a pumping lemma proof for it. Okay. That's a midterm. Right. The other thing I wanted to say is, yeah. So the other thing is I will post a midterm review guide. So either today or tomorrow. So today or tomorrow. And what it'll have on the review guide is it'll first say, what to study. So I think actually how to study more than what to study. What assignment questions to look at. And I'll also post, it'll also have extra practice problems. Okay. Right. And the other thing is that starting tomorrow, it's reading week. So you're meant to read. So tomorrow is so starting Friday all the way to Wednesday. It is reading week. So effectively what this means is that there will not be, no office hours from the TAs or from me. I'm not sure about Claude. Maybe I should ask him. From Friday to Wednesday inclusively. But I will hold extra office hours on Thursday and Friday. And what I wanted to do, so it's good that you stuck around, is I wanted to ask you what times would be best for you. So on Thursday, I can give you an extra round of office hours and on Friday as well. Is there a time that works best for people? Because I know people have 360 right after. Or you guys don't want extra office hours? Oh, you want. From 1 to 2? On Thursday? No. Okay, but I'll have one on Thursday. So let's say on Thursday, 1 to 2:30. So I think Ben. What? Oh, okay. 2:30 to 4? Okay. 2:30 to 4? 4 to 5? It depends on Friday. Yeah, 1 to 5. Yeah, all right. Okay, I don't know. TBD. Well, you want me to do a poll? I hate polls. All right, fine, I'll do a poll. Polls. All right. Any questions on this? Yeah. What? No proofs of correctness. No. Yeah. I think just come talk to me. Okay. Thanks, everyone. Have a nice weekend and a nice reading week, and see you on Thursday.
You have any informal make